Topic 4 is about waves. First section is just about oscillations in general. I'm going to be doing a brief overview of the sections in this book and anything else that seems relevant that pops up. So this first section is pretty simple. In the data booklet, there's only one equation for this first section, although I would argue there should be more than one equation. So it's just all about oscillation. So what is an oscillation? Something that is, typically we're talking about periodic oscillations. So something that is a regular pattern that happens. Now a heartbeat could be considered a sort of periodic motion, but that is not a simple periodic motion. In this class, we're talking about simple periodic motions or simple harmonic motion that is executed by a simple harmonic oscillator. So something we'll have, so if we have a pendulum swinging back and forth, it will swing, if we lift it up to here, it will swing through the bottom to the very top. That's a half of a period, and then it swings back to where it started. That's a full period. There and back again, a full cycle. Now it gets a little bit weird if you start in the middle and you kick it, and then it goes that way, and then back to where it started again. It would not be a full cycle because it hasn't done the movement to the left in that case. You need to cover every single portion of one full cycle to get a period. Actually, they have a few examples of oscillations here. Now, are all of them simple harmonic oscillations? Let's see. Motion of a mass in a horizontal spring, yes. Motion of a ball inside a round bottom bolt, yeah, pretty much, depending on the shape of the ball. Vertical motion of a body floating in liquid under the action of wind and waves. No, that probably wouldn't be simple harmonic motion. It is a harmonic motion or an oscillation, but not simple harmonic motion. A tight guitar string that's set in motion by plucking the string, yes, for individual particles. The motion of a diving board as a diver prepares to dive, yeah. Well, after the diver jumps off and the board goes boom, 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 like that, yeah. The oscillation of an airplane wing, yes, that would be driven periodic motion. That would be a driven oscillation. So a little bit different, more complex than what we cover. And the motion of a tree branch or a skyscraper under the action of a wind. Yeah, although those would generally be damped. Now, there are a few characteristics of this simple harmonic motion. One is the period that we talked about. And of course, period's the amount of time it takes to do one full cycle. But there's also the frequency of that cycle. So the period is a capital T, and frequency is 1 over that. That's the only equation you have for this section, because period is the amount of time it takes, whereas frequency is the number of cycles per second. So a higher frequency means faster oscillation rate. A higher period means a slower oscillation rate. And then, of course, you have the amplitude. So how far does it swing either way? In the case of a pendulum. In the case of a mass in a spring, that's what is its maximum distance from the equilibrium position. Now, all simple harmonic motion has an equilibrium position. Where is that? That's where the object wants to be. That's where the net force on the object is 0. So right here, the spring is the length it likes to be. If you have a ball just hanging right there, gravity's pulling down, the string's pulling up, net force is 0, it's perfectly happy, no motion, it's perfectly happy. Now, if it is swinging, then at that point, it does not have a 0 net force. Well, it has a 0 net force in that direction acting on it, but in that case, actually, the force from the string is going to be a little bit bigger than the force of gravity, so you can have a circular motion through that arc. Now, simple harmonic motion is defined by this relationship right here. So for simple harmonic motion, it's defined by a restoring force. So this is the way I define simple harmonic motion in class. So you have a restoring force. That negative sign makes it a restoring force. That means if I displace the object to the right from equilibrium, the force is going to pull it back to the left. It's always trying to restore it to equilibrium. If I push it to the left of equilibrium, the force is going to go to the right, trying to restore it to equilibrium. Not only does it go the opposite direction of your displacement, but it gets stronger the more you displace the object. And it does so linearly, right? This is not squared. It's not 1 over delta x, where delta x is your displacement. It's not the square root of delta x. It's just delta x, which means that if I have my force, and I'm just going to do the absolute value of force and displacement, it's linear. So if I double the displacement, I double the force. I double the displacement, I double the force. So those two things, restoring force and linear, are what make simple harmonic motion. Okay, so any periodic motion that's caused by a force that is a restoring force that is linearly related to displacement will cause simple harmonic motion. Now, they also give us this, so that acceleration is proportional to the negative delta x, the negative displacement. They just use an x. I like to use a delta x to make it very clear that we're talking about a displacement, not a position. So that is a consequence of this. So for example, if this is a net force, this force is our net force. For example, with our spring here, the spring force is our net force. So I can say then, okay, then the net force is equal to the spring force. That's MA is equal to negative K delta X. Well, these are constants, so they don't matter for proportion. So I can say, yeah, acceleration is proportional to negative delta X. These are both vectors, of course, and those are vectors. Now, what are some other characteristics of simple harmonic motion? Period and amplitude are constant. You can have damped motion in which the amplitude gets smaller over time. You can have driven motion in which the amplitude gets larger over time, but we don't really cover that in SL. The period is independent of the amplitude, right? So if I displace this box to there, or if I displace it to there, the period is the same thing. Why would that be the case? Well, if I displace it to here, the overall average acceleration is not very big because I haven't caused a very big displacement. But if I displace it all the way over to here, the restoring force is very large because I have a larger displacement. Therefore, the average acceleration will be much larger. So it'll cover that same distance, or that larger distance, in the same amount of time because it's got a larger acceleration. And its acceleration is larger in just the right amount. Now, one thing also to keep in mind, you cannot use our kinematics equations for constant acceleration here because this box right there, if this is the amplitude, x equals a for amplitude, this is the maximum displacement. Here it's got maximum acceleration. Right here, the spring's applying less force. That means less acceleration, so you have a non-constant acceleration here. Now here they're going over a little bit what I just went over with the equation for the restoring force. And this graph gets students frequently. All right, so this is just a graph of this relationship right here. This graph just covers this let's see. Okay, this covers this relationship right here. So if I've got displacement and acceleration, that should be right through the origin. I missed it a little bit, but it's always linear with a negative slope. And it goes from negative amplitude to positive amplitude. And the steepness of that slope will be based on the K value and the mass of the object. Why is this the case? Because this is the case. Acceleration is proportional to the negative of displacement. So when displacement is positive, acceleration is negative. When displacement is negative, acceleration is positive. So this line always has a negative slope. It's always a straight line. So every simple harmonic motion is just moving along this line, back and forth, back and forth, back and forth. Now, because simple harmonic motion is so simple and periodic, we can describe it with trigonometry. And so that's what these graphs are. Right? As the object bounces up and down, this might be its vertical or horizontal position, maybe something going side to side, in which case this would be the horizontal position as a function of time. Now, what about its velocity? Well, its velocity follows the exact same rules we use in kinematics. So the velocity is the slope of the position graph. So if you just look at the slope of that graph, look, the slope starts off at 0. And then the slope gets more and more negative. Velocity starts off at 0, and velocity gets more and more negative. Slope reaches 0. Velocity reaches 0. So you might say, well, what happened from here to here? Sorry, I kind of skipped that. So we start off with 0 slope. It gets more and more negative. The slope gets more and more negative. Then the slope gets less and less negative to 0. So velocity gets more and more negative from 0, and then it slows down to 0. So that 0 is that 0. That 0 slope is that 0 velocity. And then it does the opposite in the opposite direction here. That's this bump. And then it goes negative again with the slope. So that's this bump, and so on. For those of you in calculus, you can just use derivatives. And then acceleration follows the exact same rule again. And you'll notice that the acceleration graph is a cosine graph, a negative cosine graph specifically. This position graph is a positive cosine graph, whereas this is a negative sine graph. If this is a positive cosine graph, this will be a negative cosine graph. If this was a negative cosine graph, this would be a positive cosine graph. If this was a positive sine graph, this would be a negative sine graph. It always goes to the same trig function. We only have two options, sine and cosine. It always goes to the same trig function and changes the sign from position to acceleration. Almost like it's related to this. Same shape, but opposite sign. Now, the equation for one of these lines is going to be, I'll do the position. Position as a function of time is equal to the amplitude times, they did a cosine, I'll do a cosine. You can do sine or cosine, omega t plus phi, where omega is the angular velocity. You may remember that simple harmonic motion is just like uniform circular motion. If we have something going in uniform circular motion, as viewed from the side over here, it looks like it's just going up and down in simple harmonic motion. So this omega is the angular velocity that that object would have. Angular velocity meaning what angle it sweeps out each unit of time in radians, specifically in radians. So this is angular velocity in radians per second. Radians per second for that. Now, to get the VT graph, the velocity as a function of time, that's going to be a omega, negative a omega sine of omega t plus phi. And then the acceleration graph would be negative a omega squared. Not sine, but cosine. Uh-oh, I don't have an eraser. Cosine of omega t plus phi. Now, t is time, obviously. Omega is that angular speed, and omega is related to the period. So the period is going to be 2 pi divided by omega. This is where we get all of our equations for period, for a pendulum, for a mass in a spring in simple harmonic motion. Are those in your data booklet? They are not. But I'll give them to you anyway. The period of a pendulum is 2 pi square root L over G, and the period of a mass on a spring is 2 pi square root of M over K. What that means is that omega for a pendulum is equal to the square root of G over L. Why did it flip? Because omega is in the denominator. All right, so when I write it like this, I just flip and multiply. And omega for a mass on a spring is equal to the square root of K over M. And that's what would go into your equation here. Do you need to be able to do that for this class at the SL level? I don't think you do, but it's just a little bit of extra. Now, what about this phi, though? Phi, it's a Greek letter phi, not phi, but phi. So what's going on there? Oh, and let me just write, this is omega, a lowercase omega. So what is the phi? Phi is phase difference. So if you look at these three graphs from sine to cosine and something in between, they're the same shape. They're just shifted by some angle. And that's what the phi is. Interestingly, sine and cosine are the same graph, just shifted by 90 degrees. This is why the cosine of 90 degrees is equal to 0, while the sine of 0 degrees is equal to 0. And so they're shifted by 90 degrees, and that's all that phase angle is. If you have more questions about it, please let me know, and I can cover that in more detail. But one more thing about phase difference is we will talk about this when we talk about interference. All right, so if two things are in phase, that means their waves are lined up, so we're going to get constructive interference. If they're perfectly out of phase, that means their waves are 180 degrees. The phi would be 180 degrees in this case, because that's half of a period. Right? A period would be that for a sine graph, or that for a cosine graph. Those are very ugly, I apologize. And these would give us destructive interference, but that's getting ahead of ourselves. So state whether these represent simple harmonic motion. No, the period is changing. It's getting shorter. The frequency is increasing. Yes, because this is our acceleration is proportional to negative displacement. Yeah, actually, I think the amplitude's getting smaller on this one. So as defined, no, this is not simple harmonic motion. This is damped harmonic motion. And then this one, I don't think you can look at that yourself, because the answer is right there. Now, energy in simple harmonic motion. So simple harmonic motions, we have a certain amount of mechanical energy in the system, and we're just keeping that constant. It's just shifting between kinetic energy and potential energy. So if we've got a mass on a spring, I'll call this the equilibrium position x naught. It'll go to negative a and positive a, which are hopefully pretty close to the same distance away. What I can do is I can analyze the energy and the force and the acceleration and the velocity in all these different places. So obviously maximum displacement there, minimum displacement there, maximum displacement there. What about the velocity? Well, the velocity here is 0, because that's where it's turning around. Here at equilibrium, it's maximum because it's been accelerated the whole distance from the amplitude to the equilibrium position. Here, the velocity is 0 because it's turning around again as it goes back and forth. The acceleration, well, here it's at its maximum because the spring is applying the largest force. Here it's 0 because the spring's perfectly happy right there, and here it's maximum again. What about the, actually, let's say the force. Well, that would mimic the acceleration because of Newton's second law. What about the kinetic energy? Well, the kinetic energy would be 0 here, maximum here, and 0 there. It will mimic velocity because it's equal to 1/2 mv squared. V is the only variable. What about potential energy? In this case, spring potential energy. I don't remember if in class I use a PE for potential energy or a U for potential energy. Same thing. Well, the spring is compressed there and stretched there, so we're going to have maximum spring potential energy in those locations and 0 spring potential energy there because it's not stretched at all at the equilibrium position, it being the string or spring, because this is the equation and that's the only variable. Now, what's happening is we're just shifting between these two forms of energy. So if we were to draw a graph, and actually they give us the graph here, so I might as well not draw it. We have a total amount of energy in our system that's based on how much we pull the spring and how large the spring constant is, or if the mass starts at equilibrium and we get it started by giving it a kick, how hard we kicked it and what the mass of the mass is. So at equilibrium, we've got all kinetic energy. This red line is kinetic energy, but as we stretch, as this thing moves, say, to the right, the spring is stretching and applying a force to the left, slowing it down. Well, where is that kinetic energy going? it's going into the spring as spring potential energy. And however much we lose in kinetic energy, that's how much we gain in spring potential energy, so our total energy remains the same. We assume this is a frictionless system. In any system with friction, that would be a damped oscillator, which IB does not define as a simple harmonic oscillator. And then we get to the maximum amplitude where we've lost all of our kinetic energy, and now all of our energy is in spring potential energy. So we could write that our total energy, E total, is equal to PE spring maximum, which is equal to kinetic energy maximum. And of course, maximum spring potential energy is 1/2 Ka squared. Why A? Because A is the amplitude. You can say delta X max as well if you want to. And here, that's 1/2 MV maximum squared. Now, that only accounts for the extreme positions and the equilibrium. What about in between? Well, in between, we're going to have some combination of the spring potential energy plus the kinetic energy at any given location. That would just be equal to 1/2 K, I'll just call it X for now, squared, plus 1/2 MV squared. So using this, if I know the amplitude and, say, the spring constant and the mass, I can figure out the maximum speed. And then I can say, well, what about when the spring is stretched 1 centimeter or half of the total amplitude? Then I could figure out how fast it's going at any location, because I could figure out then what is the total energy in the system. I would know the X, I know the K and the M, so I could just solve for V, because I would know everything except for V. Here they have some nice worked examples, but you can look at those again on your own. If you would like me to go over those in more detail, if you have any questions on those, please ask me. Here they just talk about the exact same thing I did right here, except they say EK for kinetic energy and EP for potential energy. Very offensive. And that's it. That's the section. It's really not too bad. Maybe I'll do one quick example for you. So let's suppose, and by the way, this equation works the exact same way for a pendulum, which is another simple harmonic oscillator. But for a pendulum, it's very important that the amplitude is small. So the amplitude is small, such that the maximum angle is less than or equal to, some people say 10, some people say 20. I'll say 10 to 20 degrees. 20 degrees definitely being your maximum for that. What I mean by the angle is if we've got a pendulum, this would be our maximum angle, right? So I lift the pendulum to there and then I release it. From here, that's therefore my maximum angle. But let's return to the spring because, well, let's not return to the spring. So in this case, what kind of energies are we trading? Well, we're trading kinetic energy and gravitational potential energy. Turns into the exact same thing as this, except this changes to a gravitational potential energy, so it's 1/2, I'm sorry, not 1/2, mgh, where h is this height from the bottom here. And that can become your variable. So for a pendulum, E total would be PEG max, which is also equal to KE max, which is going to be equal to PEG plus K. So this would be mg, I'll give a capital H for the maximum height, is equal to 1/2 mv maximum squared. And that's equal to mgh, so any given height, so say there, the height would be this, plus 1/2 mv squared. Now, for something like this, the energy equation that they gave for spring it's going to look a little bit different, because if that's our zero height, we're going to have height here, and we'll have, I'm sorry, we won't have height there, we'll have energy there, and we'll have height here. And we never go to negative heights if this is our h equals 0 point. And what we're going to do is we're going to look at, because this is height, which one of these depends on height? Which one of these types of energy depends on height? Well, gravitational potential. So I'm going to look at that and see that it's linear with height. So I'm going to first draw my total energy. It's a straight line. Let's go to a maximum height here at h, and this will be a straight line from 0 all the way up to the maximum energy. Why? Because this is a straight line. And then my kinetic energy would be the opposite. So this would be kinetic energy, and this would be gravitational potential energy. Now that I'm writing all these PEs, I'm pretty sure I used U in class, so I hope that's not confusing for you. Now this looks very different. Why? Well, because this is with relation to displacement. This one was as well. This was position and energy. We had our maximum energy, we had our kinetic energy, and our elastic potential energy, PE, spring potential energy, and our KE, where this was the maximum amplitude and this was the negative of the maximum amplitude. This one's curved. Why? Well, because this is displacement, and spring potential energy is related to x squared, whereas here, gravitational potential energy is related to h. I was going to do an example with numbers here, but I think this video is probably going kind of long. You probably don't want that right now. If you'd like one like that, let me know. I can do that for you. But for now, this has been a somewhat detailed overview of Section 1. Good luck.